This is Module 4, Lesson 18, where we're reviewing linear equation, things that we've learned about linear equation in the last unit. And we're going to be comparing unit rates. Now let's remember the standard 8EEB5 has pieces to it. First, it wants us to graph proportional relationships. Proportional relationships are when we've got a linear equation where the b is 0. Okay, so we've done that, we've graphed them. This is interpreting the unit rate as the slope of the graph. We've done that. Unit rate, remember, is when you're dealing with a slope where the denominator is 1, like 50 miles per 1 hour, 13 miles per 1 gallon, things like that. What we're doing today is we're going to compare two different proportional relationships represented in different ways. We're going to work on this part of the standard. Now, our objectives today is to write linear equations from word problems and graphs. Okay, this is to go back to handle some of this. And then we're going to compare those linear equations, handle the bottom part. All of this can be found in Eureka Workbook, Module 4, Lesson 22. Okay, we're going to start here on this blank page, and I want to go over a few things. First, I want to go over linear equations. Now, we've talked about what the form is for the point-slope form for a linear equation. No, actually, slope-intercept form, so we're looking for. Y is equal to mx plus b, okay? When we're talking about y is equal to mx plus b, we are talking about a linear equation. Now remember, our x and our y are the coordinates. Those are the things that if you put in your independent variable x, you'll get out your dependent variable y. M and b are pieces that you're going to put in. P is your slope. I'm sorry, P is your y-intercept. All right, it is where you start. If you're looking at a plot, let's say we got a plot that looks like this. This would be your B, your point 0, B. It means it crosses, this is where it crosses the y-axis, okay? It's also what we call the place that we start, the place we begin if we're plotting something. If we're trying to plot something, you could start at that B, and then you can use your M to tell you where you're going to move, okay? Your M is your slope. It is, another way to just call that is to call it your rate of change. It can be known as your rise over your run, your change in y over your change in x, okay? All of those deal with slope, and what slope tells us when we're plotting something, it's where we move to. We start at our B, and the slope tells us where to move. So what am I talking about here with move? So if we had a linear equation, let's say y is equal to 2 over 3x plus 1, okay? And let's say right here we're at 1. B is where we start, okay? You can see this is y is equal to mx plus b. B is where we start when we plot. This is at positive 1 unit above the origin on the y-axis. Then our slope, 2/3, would be our rise over our run, our change in y over change in x. So from here I would go, let's put us in some place. Here I would go up 2 on the y-axis, you go in the positive direction 2. And then on the x direction, you go over 3, 1, 2, 3, positive direction 3. Okay, if I were plotting this one, then guys, it would look like that. Okay, 2 different lines here, okay? So this is our linear equation. Y is equal to mx plus b, okay? So let's start this one and let's try this one. What we're going to do on this one is we're just going to review the concepts that deal with linear equations. Okay, so this is just a review of linear equations. And remember, there's lots of ways to present data that have a linear relationship. You can have a word problem. You can have a chart. You can have a graph. a chart of, you could have a chart of values, you could have a graph. Okay, so we're going to look at some of these. Peter paints a wall at a constant rate. Constant rate means that its slope does not change no matter where you pick your points. So therefore it's linear. Constant rate of 2 square feet per minute. There is our rate. 2 square feet per minute. That means per 1 minute, right? Assume he paints an area Y. Okay, so Y is in square feet. So our Y is square feet. Tells us here, right here. After X minutes. So X is the number of minutes, right? I'm just making myself notes so I know what I'm doing. This is my rate of change. This is my slope. This is what my X and Y represent. Express this situation as a linear equation. So we want to make this look like Y is equal to mx plus b. Okay, our X and Y's are our variables. Our m is our slope. Our b is where we start. Think about this. If Peter is painting a wall, here we got a nice little wall, okay? And he's trying to paint that wall. He's rubbing on paint. Okay. At time 0, at 0 minutes, how much of the wall has he painted? Well, if you read here, it doesn't say anything about any of the wall being painted before he got started, does it? So we have to assume that he has 0 square feet painted whenever he starts. Okay? We need to find our m, our slope. We already did. Here's our rate of change, 2 square feet per minute. So 2 is substituted in place of m. Y is equal to 2x plus 0. Okay? Now, if I add 0 to something, I don't even have to include that. I could simply say y is equal to 2x. What this equation tells me is this. The number of square feet he has painted is equal to 2 square feet per minute times the number of minutes, right? So if that's the case, down here they want us to sketch this graph. Y is equal to 2x. Y is equal to 2x. I forgot to get rid of that. Hold on a second. Let me get rid of that. Okay. So y is equal to 2x. Let's plot this. We know this is our linear equation. Y is equal to mx plus b. I don't have a b here. Remember, that one was just 0. Well, that's fine. On the y-axis, we plot our b, our beginning point. It's at 0, right? Remember that point there, 0, 0, isn't it? So it says my b is 0. My slope here is 2. My rise over run is equal to 2. Okay? So from the 0, I go up 2. Look, see how these are in units of 2? I go up 2 and over. Oh, it doesn't have anything underneath there. What can I divide 2 by and not change it? You divide it by 1. So we go up 2 and over 1. Right, there's your 1. Up 2 and over 1. You can keep doing this so you got enough points that you're comfortable plotting it. Up 2 and over 1. Okay. And then we draw a line through those points so we can see our linear equation, right? There we go. Okay. The bottom part here says use the graph or the equation. Here's your equation, here's your graph, to determine the total area he paints in 8 minutes, 1.5 hours, and 2 hours. Note there are units that are in minutes and units that are in hours, so we need to be careful here, don't we? Let's make us a little T-chart for values, okay? Make it easier. This is my time, because here's on your x-axis, is time in minutes. This here is my area in square feet. Okay. At 8 minutes, okay, I can either use my equation or I can use this chart. At 8 minutes, how much has he painted? Well, you can look right here, read on the chart. This is 8 minutes. He has painted, let's go over here, what, 16 square feet. At 8 minutes, he's painted 16 square feet. Well, that makes sense if y is equal to, as it says, 2x plus 0, or just y is equal to 2x. Plug the 8 in, 2 times 8, 16, okay? Then it says, what about 1.5 hours? Well, we got to convert this 1.5 hours business, don't we? 1.5 hours. We need this in minutes because we're talking about minutes. Let's see how many minutes that is. I got 1.5 hours. How many minutes are in an hour? 60 minutes in 1 hour. Okay. 60 times 1.5 would give me 90 minutes. So you can think about it this way, guys. 1 hour, 60 minutes, plus a half hour is 30 minutes. That's 90 minutes. Okay, so for 90 minutes, I can say y is equal to 2 times 90. 2 times 90 is 180. After 90 minutes, I've got 180 square feet painted. It's because I'm doing 2 square feet a minute, right? How about 2 hours? It talks about 2 hours. Well, let's convert 2 hours to minutes. Okay. If I've got 2 hours, I know that there is 60 minutes per hour. Okay, if I multiply 2 times 60, I got 120 minutes. Okay, so how much can be painted in 120 minutes? Y is equal to 2 square feet per minute times 120 minutes. That would be 240. Okay, so after 120 minutes, he would have painted 240 square feet at that rate, right? Okay. Now that we have reviewed all the things about linear equations and even how to find values from them, we're going to do some comparisons. The figure below represents Nathan's constant rate of walking. When I'm doing comparisons, guys, I make sure I've got something to make it bold as to what I'm comparing. I'm comparing Nathan. Okay, he's doing some walking, and here's his chart. Who am I comparing him to? Nicole just finished a 5-mile walkathon, so I'm comparing Nicole and Nathan. Let's go back to Nathan. Represents Nathan's constant rate of walking. Well, let's kind of look at his rate of walking. I can read it on the chart here. The X is time in hours, the Y is distance in miles. Let's look at some of these points and see what they say. After 1 hour, he has done what? 4 miles. After 2 hours, he has walked what? 8 miles. After 3 hours, he has walked 12 miles. After 4 hours, he has walked 16 miles. So see, that tells us what's going on there, doesn't it? Let's look at Nicole. Nicole just finished a 5-mile walkathon. It took her 1.4 hours. So she went 5 miles in 1.4 hours, right? Assume she walks at a constant rate. That means we've got a linear equation. Let y represent the distance Nicole walks. Okay, distance, let's see, that would have been miles, right? Y is our number of miles. X is our number of hours. Describe Nicole's walking at a constant rate as a linear equation in 2 variables. Y is equal to mx plus b. Constant rate, okay? Linear equation. Well, if she's walking, guys, it didn't say she started, farther out. At time 0, she has walked 0 miles. Okay? We need the slope, the rate of change. Okay, wouldn't that be 5 miles per 1.4 hours? Okay, we're putting the time on the bottom. If you put that in your calculator, you're going to get 3.5 something, which is 3.6 miles per hour. Okay, I'm going to put that in for the M. That's 3.6 miles per hour. Who's walks 3.6 miles per hour? Nicole. Okay. All right, let's see what else it asks us. Who walks at a greater speed? Nicole's walking 3.6 miles per hour. How about Nathan? How can I find his speed? Isn't his speed the same thing, his rate of change? His slope? Okay, let's try that. Let's look at our data here. We know he crossed here. We know slope is change in y over change in x. Up and down over left and right. Okay, let's find 2 points. Oh, there's 2 points. From here to here, I'm going up 2, 4. So I'm going up 4. And I'm going over, look at your units here. I'm going over 1. So my slope is 4 over 1. That's a change in y. Up and down is 4. Over here is 1. See, the line is up, is sloped up. It is a positive slope. 4 over 1 means that he is walking 4 miles in one what? 4 miles, because that's your change in y over change in x, over it in 1 hour. 4 miles per hour. Who's going faster? Nathan at 4 miles per hour or Nicole at 3.6 miles per hour? Nathan is going faster. He's walking at 4 miles per hour. Explain. Nathan is walking at a rate of 4 miles per hour, while Nicole is walking at a rate of 3.6 miles per hour. Okay. Now let's look at number 3. It's on workbook page 269. Susan can type 4 pages of text in 10 minutes. Assume she types at a constant rate. That constant rate thing tells us this is a linear equation. Write the linear equation that represents the situation. We're going to model the situation with the linear equation. We start with y is equal to mx plus b. That's our linear equation. Our b is where we begin. When she begins typing, how many pages has she written? How many pages has she typed? 0. Okay, so it's a proportional relationship. Your b is 0. Now we need our slope. Okay, your slope is your rate of change. 4 pages in 10 minutes. 4 pages in 10 minutes. Okay, if you divide that, you're going to wind up with 0.4 pages per minute, or 0.4 page per minute. In other words, less than half a page per minute. 4/10 of a page per minute. Okay, there's our equation. Here is her rate, 4/10 of a page per minute. Okay. This is for who? Susan. We're comparing Susan's rate of typing to whose? We're comparing it to Anne. The table of values below represents the number of pages that Anne can type, Y, see pages typed Y, and a few selected minutes, X. Assume she types at a constant rate, so it's a linear equation. Who types faster? To decide who types faster, we need the slope. We need the rate of change. We know that a slope is change in Y over change in X. Here's our Y's. So we're going to say 10/3 minus 2. Put that in your calculator. 10 divided by 3 minus 2 gives me 1.3. My change in Y is 1.3. Now let's find our change in X. Here's our X. This is 5 minus 3, which would give me 2. 1.3 divided by 2. If I divide 1.3 by 2, I get 0.6 something. So my slope is actually, if I'm doing it as 1 decimal place, it's going to be 0.7. 7/10 of a page per minute. Okay, this is 1.3 pages per 2 minutes, 0.7 pages per 1 minute. Okay, so who is typing at a faster rate? Yep, that would be Ann, because 0.7 is bigger than 0.4. Who types faster? Ann. Okay. Let's see. Susan types at a rate of 4/10 pages, 4/10 of a page per minute, while Ann types at a rate of 7/10 of a page per minute. 0.7 is greater than 0.4, so Ann types faster. Okay, here we go. And then let's look at page 269 through 270. Phil can build 3 birdhouses in 5 days. Assuming he builds birdhouses at a constant rate, write the linear equation that represents the situation. Okay, so we're going to do our linear equation. Y is equal to mx plus b. Our b is where he starts at. How many birdhouses does he start with? Doesn't tell me he has any, so it's 0. Y is equal to, and our m is our rate of change. 3 birdhouses in 5 days. Okay, now if we made this into a unit rate so we could compare them, I would divide 3 by 5. If you divide 3 by 5, you get 0.6, okay? So this says that he is building 6/10 of a birdhouse each day, okay? A little more than half that birdhouse each day, right? Here, this goes into your equation right there. And you don't have to have the 0 in there. You can put that as 0. Y is equal to 6/10 times x. This would be the number of days, right? Number of birdhouses is y. B, the figure represents Carl's constant rate of building the same kind of birdhouse. Who builds birdhouses faster? Okay, so let's find his rate. And let's find where it crosses. Oh, here it is. Here's a good place. Okay. This says in 4 days, he builds 3 birdhouses. His rate would be rise over run, change in y over change in x. And this is going up 1, 2, 3. So we went up 3. And over 1, 2, 3, 4. And over 4. 3 over 4. Up 3 over 4. If I divide 3 by 4, I'm going to get a rate of 7,500 birdhouses per day, right? Okay, so who is building at a faster rate? 0.6 or 0.75? Okay, that would be Carl or Phil. Carl's building faster, right? Carl builds at a rate of 0.75, 3/4 of a birdhouse per day. While Phil builds at a rate of 6/10 of a birdhouse per day. since 0.075 is greater than 0.06, Carl feels faster, right? All right. Now, what are we actually comparing each time? What have we been comparing? When we've compared these, explain your general strategy for comparing proportional relationships. What have we been comparing? Compare the slopes, right? That will give you your rates. You can compare your rates. When given information about two proportional relationships, determine which one is less or greater by comparing their slopes, their rates of change. Now, this problem set, I'm going to do this separately as your homework. What we have learned is that if we're trying to compare proportional relationships, we need to find the slopes and compare the slopes.